Okay, so it's a pleasure to have Hari Karan visiting from Technion. Hari will tell us about some new results he has on backtones, or maybe related to some older work other people did. Yeah, I'm looking forward to having some unique perspective.
Yeah, this is really, so I'll explain the fractals. We haven't learned about it before, but it's something basically invented by John Wilcox. And he also has, in the original paper, it's kind of complicated case-by-case algebra that he has to do to explain the properties. And then he has a later paper where he fitted into some algebraic framework, which is kind of elegant, but it's also hard to understand. So I'm going to explain it a little bit more with examples. But it's basically all his work. I just have to organize some things. Okay, so what John Wan discovered, what I discovered, is that there's a Hamiltonian which has the property that there's excitations of that Hamiltonian that can't move. And it's not real like Anderson localization or something where they're just trapped by disorder. Even if you apply an external field to give them energy, they can't move because there's no operators that could move them. So it's a kind of a, sometimes in some papers he called it a glass, but it's like it's a quantum glass that where the excitations are somehow entangled so much that they just can't move from the place where you first create them. So I would just write down, I want to explain that property, but I want to write down the Hamiltonian. So the Hamiltonian is a three-dimensional lattice, and at each side of the lattice, you imagine you have 2.5 degrees of freedom, and then for each cube, you have an interaction between all the 16 spins at the corners of the cube. So that's a lot of spins, but it's not. So it's not very realistic to actually happen, but it's just interesting. So what is the interaction? So there's two terms for each cube. And each term is a product of either sigma x's at the corners of the cubes or sigma z's at the corner of the cubes. So the sigma x's, I'll write it like this. So the first term, you take the first qubit at these three corners and multiply the sigma x's together, and the second qubit at these four corners and multiply them together. So altogether you get 8 sigma x's multiplied together. So I'm just writing which at each corner do you use the first or the second sigma x for that corner.
But you mean z, is that?
No, that's a 2.
Oh, it's.
So it's the second sigma x2 at these three corners, and then there's no factor for this corner. Then for the other corner, it's kind of the same thing but upside down for the sigma z interaction. I want to write it out. This is the axis and this is I could write it out like this. H equals minus second. EI goes from 1 to 3, representing the 3 directions, the x, y, and z unit vectors. So for each term has 1 factor of sigma x1 and 1 factor of sigma x2 for this corner, then 3 factors of sigma x1 for the corners 1 unit vector over, and then 3 factors of sigma x2 for the vectors for the corners that are 2 units over. And similar thing for sigma z. So that's the Hamiltonian. It looks really complicated, but one thing you can check is that every term of the Hamiltonian commutes with every other term of the Hamiltonian. So you can describe the ground states by just saying the eigenvalue of each term. Since each term squares to 1, that means the eigenvalues have to be plus or minus 1, which means the energy would be minimized if all the terms have a value of 1. So that's how you can describe the ground state, is by just saying each of these products is equal to 1. And if you would just look at one term, that's sort of a simple condition. You just arbitrarily choose the eigenvalue of sigma x1 and sigma x2 on each site in such a way that all these products can come out to 1. And there's many ways to do that. As you can see, because there's 2 sigma x's per site, and this condition only gives one condition per cube, and it's the same number of cubes as sites. So you have like 2n plus or minus 1s, and n relationships between them. So there'll be about 2 to the n different combinations that satisfy those relations. Does that make sense?
Can you just write out what you said?
So I have, if I focus on the first term, imagine there's n sites. Or let me say it's an n by n by n cube, so there's n cubed sites. The first term gives n cubed relations. Between 2n cubed plus or minus 1s. So you can see, if I think about it like algebra, like linear equations, I have fewer equations and relations. To make it more precise, I can actually make that connection more precise by thinking of the values, instead of thinking of them as being multiplied together, I can think of them as being numbers modulo 2, which are each 0 or 1, and I add them modulo 2. Because if you say sigma x is minus 1 to the n, where n is 0 or 1, that's another way to describe these values. So this is, if I write sigma x I of r equals minus 1 to the u I of r is 0 or 1. And I have n cubed linear relations between 2 n cubed variables. So if they're independent relations, I should have an n cubed dimensional solution. Or in other words, I have n cubed unconstrained variables. But each unconstrained variable, since it's only modulo 2, has two possible values. So that implies there's about 2 to the n cubed solutions. So if the second term also involves sigma x, it would be the right number of terms to restrict it to a unique solution. It doesn't involve sigma x, but it still works out. It's quantum mechanical, and rather than constraining these further, it forces you to make a superposition of them. And it's enough terms that basically forces them all to be superimposed with a certain coefficients, and that makes a unique ground state. let me just say some properties of this Hamiltonian. So the first property is, it has excitations that can't move. That's the first property. And it, no matter what you do, it's not, because all the terms of this Hamiltonian commute with each other, any excitation you would make won't move. It'll just stay there, just dynamically. There's no hopping terms in this Hamiltonian. Every energy is an integer, so there's no dispersion, so there's no motion. But that's not what I mean. Even if you perturb the Hamiltonian a little bit or add an external force, the excitations just can't be moved, no matter how hard you try. So that's the first statement. The second statement is that, well, actually the excitations can sort of move. But it's a very crazy kind of movement. So if I start with an excitation here, I can, in one step, I can move it from here to a triangle that's displaced sort of by 1 unit upward in 3 dimensions. And then in a whole bunch of steps, I can replace it move it over to a triangle that's 2 times as big and 2 times as far away. And then in twice as many steps as that, I can move it to a triangle that's 4 times as big. So I can keep expanding those 3 excitations exponentially. So I turn this one excitation into 3 and then move the 3 out. But between each pair of steps, there's many, many operators you have to apply. And if you apply them one at a time, in the intermediate stage, there's lots of excitations. So energetically, it's very unlikely for that to happen because there's a big energy barrier. You could do it all at once and with no energy barrier. But there's no chance that it'll happen spontaneously.
Sorry. Going from 1 to 3 requires additional energy, right?
Yeah, from here to here, there's an extra energy.
Okay.
But then after that.
Alright.
Yeah. But if you did it one operator at a time, you'd create more and more excitations, and then you would annihilate a bunch, and you'd end up with 3. And then you create more and more and more, and then you'd annihilate them, and then you'd end up with 3. And in the middle, it's like the pattern of excitations is a sort of Sierpinski gasket, I think. You get some fractal pattern of what the excitations are, which is why this is called fractals. And the third neat thing is if you look at the degeneracy of the ground state. So I said there's a unique ground state. But it's actually, I was ignoring the possibility that there's relationships between the terms. And there's not that many relations. There's not an extensive number of relations, but there are some relations. So there's a degeneracy of the ground state. And that may be a topological degeneracy. Like in a 2-dimensional toric code, you have 4 ground states. And that's related to it's not just an axis, it's related to the properties of the phase. So this is interesting to look at the degeneracy of the ground state here. So I'll just make a table of, for a cubic, periodic cubic. If you take a cubic shape and you take this model with periodic boundary conditions, what's the degeneracy of the ground state? This is from Haas paper. So here's the different sides of the cube. And the degeneracy is always a power of 2, so I'll just say what power of 2 it is. 2, 6, 14, 2, 6, 2, 30. No. to 14. 2, 6 to 30. 6 to 2, 6. What's the next one?
For 15, you mean?
Yeah. 50. And then 62. Etc. So as you may notice, that at least this you may notice, that the odds usually are 2. The multiples of 2 that are multiples of 4 are usually 6. Like 2, 6 is 6. 10 is 6. 14 is 6. Then the multiples of 4 are 14. The multiple of 8 is even bigger. But every once in a while, something that has only odd factors is extra big. So the pattern is a little bit irregular.
Is there a pattern?
There's a, I don't know if it's a pattern. I mean, there's a way you can find the answer.
Ari, what happens to the excitations of the boundary?
Oh, and then I'm just looking at periodic boundary conditions. I don't know what happens actually if you don't have periodic boundary conditions.
So you say one, it's just one side? This is the,
Yeah, just one site. I don't even know. You think of this site as being all the same site. So you would end up just getting
There's no
identity. Yeah.
and that's why the DJs used to have.
Then you have two bits on that side. So then the fourth property is this one is more specialized. There aren't any.
Ari, just a question. So when it's 1 mod 4, is it ever different from 2?
I think maybe, but I don't think so.
It's the 3 mod 4 that's weird.
I mean, I think a 1 mod 4, if it has 2 factors, that a 3 mod 4. What it has to do with the factors. So it gets bigger with certain, if it's divisible by 15, it's bigger. And if it's divisible by 63, I think it's bigger. So that's why that happens.
The n minus 2 is somehow.
Yeah. There aren't any sine powers of 2 and things that are 1 less than powers of 2, any factors like that change the thing. There aren't any string operators connecting the degenerate states. Good for memory, for quantum memory. So what I'm saying here is that in the Tora code state, you have 4 degenerate ground states, and they're nice because you can't get from one to the other with just local operations. So that makes it very stable. But if it's at a finite temperature, there's a chance there'll be some finite density of excitations because of the temperature, and then they can diffuse around, and they might go periodically around the square from one side to the other side because of the periodic boundary conditions, and that will turn one ground state into the other ground state. But in this case, because excitations can't move, there's no operator that does that takes an excitation and moves it around the boundary and back to the beginning spot. So there's no operator that can turn these states into one another. That makes it much more stable in principle for quantum memory. I think there's an argument which I don't understand, which is I think due to Phantasmagoric that says that actually it's not as good as it's supposed to be. I think at low temperatures it would take much longer time for it to go make transitions between the different degenerate states, but it's still not like perfect, which it sort of sounds like, because this is saying even if you have excitations, they can't move.
Yeah, so if there are no string operators connecting them, like it's good for quantum memory, but how would we, like, say if we wanted to use it as like error correction code, how would we perform operations on like the quantum memory?
Like if you wanted to create it in a certain state.
Yeah, like if we just wanted to perform like a quantum gate, like how would you?
Yeah, that's a good question. I think there's operations that are like on surfaces. So you couldn't just go along a one-dimensional line. You could apply operators along the surface. That would get you from one state to another. But that wouldn't happen spontaneously because the energy in the process of doing that, the energy is the same story about why this won't work spontaneously. The energy would increase too much. So, and then one question which is interesting to ask, which I don't think people have looked at too much, is are these properties robust if you perturb the Hamiltonian a little bit? Will this degeneracy, it obviously won't stay the same on small sizes because you always have to have a large size, but will this exact pattern stay the same? This crazy number theoretic pattern, will it work once the system is large enough? And will the excitation still be frozen? So I want to explain why the excitations are frozen. So I'm going to look at a model that's sort of like Haas, which is the toric cone model. It doesn't have the property that the excitations are frozen, but it has a little, sorry, that's not what I meant to say. I'm going to look at a three-dimensional model that has some of the properties that the excitations are frozen. But it's a little boring compared to Haas. It's not really boring, but it's not as frozen. So what I'll do is I'll take a bunch of planes, just parallel planes. On each plane, I'll have the toric cone model. So let me write that down. What that means I have a plane, a lattice, and here I'll have a spin on each edge instead of on each side. And H will be the sum overall, either overall vertices and overall squares. So I'll have a term which I'll call vertex I. It's another term which is square I. And vertex I, like the term associated with this vertex, is the product of the sigma axis around the vertex. And square I is the product of sigma z's around the edge of the square. And I'm only taking the horizontal vertices and horizontal squares, so there's no interaction between different layers. So, what do I want to say? So just like in this model, let's try to understand this. If you know the toric code, you'll know all of this, but I just want to review it. Each layer is independent, and these terms all commute with each other. So this term tells me that the product of the sigma x, to minimize it, the product of sigma x is on 4 bonds coming out from the site has to be 1, which means you have to have an even number of bonds that are minus one. So I can represent that graphically by, on each bond, I'll color it purple if the bond is minus one, and I'll leave it white if it's plus one. So here I color all the purple. So does that minimize the first term? The way I draw the oranges? No, because I need to have an even number of oranges coming out from each vertex. So if I draw something that minimizes the first term, it's going to have to be be made up of closed loops of orange string. That's the only way to minimize the first term. It's just like what I said about the Haas model. There's many solutions to just the first term, because per unit cell there's two qubits, one on the vertical edge and one on the horizontal edge. And this gives you only one condition per unit cell. So there's many ways to satisfy all those. But if you want to satisfy the second term says, if I take something like this, and I apply this second term and I want it not to change the state, that means what the second term does is it applies sigma z, which is flips the value of sigma x, which means that I'll take, for example, if I apply the square on this place, I'll move this edge, these three edges to this edge here. So what the second term does is it takes any path and it moves it a little bit. So to be an eigenvalue of the second term for every I, you have to take every single path and superimpose it with the second coefficient. And that makes a unique ground state up to some topology. So what are the excitations of the state? An excitation, you maybe usually think of an excitation as what happens when you excite it. Like if I apply an operator to some site, what happens to the state? That would give you an excitation. But I'm going to define it a different way. I'm going to, and the reason is because there's simpler excitations that you can't make by applying just one operator. So when I define an excitation, so I'll just look at these terms, and if a term is equal to minus one, which means that there's an extra energy at that vertex, then I'll say there's an excitation at that vertex. Do the same thing for the square. So an excitation is just an endpoint of one of these curves. The ground state, all the curves are continuous, and you can have an excitation. You have like an orange curve that goes off like this. That's an excitation. And the energy of that is 2J. So I'll define EI as just this another name for the operator associated with the vertex. If it's minus one, there's an excitation. If plus one, there's no excitation. So these excitations aren't like in Haas model where they can't move around. I can move them by, if I just apply, to move it, I just have to slide this end of the string, which I can do by just applying sigma z on this edge of the vertex. I'll move over. So I can just kind of take the string and slide it along the floor, and it moves. But there's a similarity to Haas model in that if I put energy in, it can't make an individual excitation. So I can move excitations once they're there, which is more motion than in Haas model. But if I put in energy, it won't make an odd number of excitations because you can't just make it up. It's not an energetic thing. It's just not possible to make an odd number of excitations because an excitation is an end of a string, and you can't make an end of a string without making a whole string. It's not like an opiate string where you can have just one side. So what you can do though, is you can make, starting from nothing, I can make a string that connects these 2 points, which is like 2 excitations, and then I can lengthen the string until the excitations are far away from each other. And because of this term, the state already has a bunch of strings in it, so there's no energy cost to doing that. So the 2 ends of the string can be arbitrarily far apart. And for that reason, you can think of them as 2 independent excitations that can move around, and you can create them in pairs. You can create them in pairs, but they can move independently. Okay, so that's what happens in a plane. But now I said we have a bunch of parallel planes. And one thing that can't happen is excitations can't move from one plane to the other, because these strings are only defined along the planes. There's no variables in the vertical direction. The strings have to stay within a plane. That means if I have a string with an endpoint here, I can't move the endpoint up, because it's conditioned that the strings have to be continuous. It's true independently in each plane. If I want to say it, I'm going to say it more precisely because it's a generalized to the Haas code. So in each plane, I can take a circle and look how many. I want to explain why the excitations can't move between planes. I can take a circle and count how many strings cross that circle. And depending on the parity of the number of strings, I know the parity of the number of excitations inside. So I can think of that like a flux, if you like. The flux or a circle in each plane is conserved if you only apply operators somewhere inside of the circle. And that means the parity of the number of excitations in each plane has to stay the same, which means an excitation can't just move from one plane to another plane. Determines number of excitations, parity of excitations. That's not, I'm going to now give a different argument, slightly different argument, and this slightly different argument will be easier to generalize the Haas model. So the different argument is, if I just take all these EI operators that tell you where the excitations are, and I multiply them together for all the vertices in this lattice, I just get the identity operator, because each edge is associated to 2 vertices, and when you multiply them together, it cancels out. So the product of EI in each plane is equal to 1. Which is to say that you have to have an even number. You can't have an odd number of excitations in any plane. You have to have an even number of excitations in each plane. And then that means, so I could have 1 excitation here and 1 excitation far away. And then you might think, if it's a normal excitation, they can move independently in the plane. And you might think they could also move independently up and down. And if that were possible, then you could move 1 up, and the other would still be down. So you'd have an odd number in 2 planes. So that's just not possible. So that implies if an excitation can move at all, there's no way that if it can move in a local way, there's no way it would force some other excitation far away to say, oh, this other excitation move, we have to move at the same time. So this implies excitations
what happens to the spins that are on the bonds between your planes?
There's no bonds between the planes.
So you just have disconnected.
Yeah.
Oh, okay.
Yeah, it sounds really boring.
So it's literally a stack of 2D torque codes.
Yeah. So another way to say the whole thing is that because the excitation can't be eliminated, the only way to move it from one plane to another is basically to eliminate it from one plane and move it to the other because there's no operators connecting them. And you can't do that.
I guess you could introduce spins between the planes on those bonds as long as the coupling is weak, the conclusion doesn't change.
Yeah, right. All these properties are supposedly robust to small perturbations. So if I add spins on the bonds that maybe they're just paramagnetic or something, they're just fixed to a certain value, and then start to add couplings, but weak, it won't change anything. That's why it's surprising. You can understand. Let me say why. Roughly, if I make a small perturbation, these excitations are still not local things. They're ends of strings of some texture in the wave function. So you just can't move an end of a string. You have to have the whole string.
What's the form of interlayer hopping again?
What's that?
What's the form of the interlayer hopping?
No, originally there's no interlayer hopping.
But like now, if we introduce, or what should it be where it's?
Like I could add just maybe like the product of sigma-axes on two bonds that are parallel to each other. And if the coefficient is small enough, it won't make a difference. Because like what makes this state possible is that there's no energy cost to having a long string. And if I make it, as long as it stays within a plane. And if I make some fluctuations that let it go up and down, it will still like there won't be enough to make it completely, the whole string everywhere at once to completely tunnel up and down between the planes, something like that. So you still have independent planes. So just before I go to the Haskell, the reason why this looks a little bit similar to its first, excitations can't move, at least in one dimension, in one direction. And second of all, in each plane there's a degeneracy fourfold. So you have a degeneracy that goes like 4 to the n. And if you look at the table, it's also, the degeneracy is also going roughly as 2 to something proportional to the size of the cube, but with complicated oscillations. The maximum at any given size is basically 2 to the size of the cube. Okay. So, what time is it? Oh, 40. Okay. So let me, I'll first explain why this is kind of the main focus, which is why the excitations can't move. But I'll first explain why they can move. It doesn't make sense. I'll explain why they can move in that exponential way. So, so imagine you have an excitation. So just like in the torque code model, for each cube, I have the 2 terms from the Hamiltonian. And if I take one of these terms, if it's equal to -1, I'll say there's an excitation of the x type in that cube. And if this term is equal to -1, there's an excitation of the z type in that cube. And then I want to see, can I just make one excitation? That's the first question. And to do that, I'll just apply sigma z at this site, for example. So sigma z at this site, the first sigma z at this site, anti-commutes with this x operator from the Hamiltonian. It flips the sign of this sigma x, so it changes the product. And it'll change if I take any cube where the term involves that particular sigma x, that cube will be flipped by applying the sigma z at this site. So from that I can figure out that there'll be 4 cubes that are flipped, and they're in a pattern like these represent the centers of the cubes. If I apply sigma x here, sigma z here, it flips this cube. And then I translate this cube over in all 8 directions to get all the cubes that meet this point. And anytime there's a 1 at the vertex that it slides to, then that cube gets flipped. So I get 4 cubes that are flipped in this pattern. So I can make this pattern of vertices. And that means, so I can make 4 excitations like that. Or an alternative thing I could do is, if there were an excitation here, and I apply the same operator, it just changes every cube. It changes the parity. So if there's an excitation here, and you apply that sigma z, now there'll be no excitation here and 3 excitations here. Have you seen the game Lights Out? It's a, you have, this is basically what this is. So there's a grid of buttons that they light up. And if I press a button, it goes from being dark to being light. And also the 4 buttons next to it change from on to off. Whatever they are, it switches each time. So if I press this, so I can start with a set of lights, and then I try to figure out which buttons I have to press to get all the lights off. So this is basically the same problem, except with some more complicated rule than we have. In this case, you press this button, you get a plus sign. And that characterizes the problem. Each button you press, you get a flip of the parity of the lights on the plus sign. And in this case, you press the button and you get a flip on the 3 quarters. It's slightly more complicated because there's 2 kinds of buttons you can press. You can press button 1 or button 2. And also is that right? No. Yes. So there's only 1 light in each cube, but there's 2 kinds of buttons you can press. And if I want to solve this, if you ever try to do this puzzle, it's very annoying and hard to figure it out. But I can give you a nice algebraic way to do it. So if I have say in general, that if you So if I have a Hamiltonian that has at each cube labeled by a vector r, I have a certain number of x terms. In Haas code, there's only 1 x term, but in general, you might have several. And it'll be a product of sigma x's displaced by certain vectors and raised to a power which is either 0 or 1, according to whether you want that term or not. I can represent represent the Hamiltonian by a set of terms like this?
It's one term in the Hamiltonian, one of the two terms.
Yeah, and this, for Haskell, there's only one term. But you might have several sigma, you might have several x operators in a more complicated Hamiltonian.
But you're not doing the z term, you're only doing the x.
Yeah, I'm only doing whatever the x term is. It's something similar for the z term. That's something the way I'm talking about it is going to look mostly classical because I'm only focusing on x terms. But it's sort of, you don't really have to think about it. So if I apply, so here I have mu is representing which of the two spins, or which of the however many spins on the lattice you're dealing with, and alpha is which term of the Hamiltonian. There might be several terms. If I apply now the sigma z operator, the mu sigma z operator on site R, this will flip. This will take ER it'll take ER minus D. To the opposite side. If n alpha mu is 1 by 2. So this is, it'll flip any, to say it in just English, it'll flip any term, which includes the sigmax, the corresponding sigmax. So if I look at these n's as a function of d, it gives me a pattern in space which describes which of the vertices are, which of the cubes are going to flip side. So I can represent that pattern. A nice way to represent that pattern is by taking a function of 3 variables. Times n for each alpha mu, I have a function like that. So I'm just taking the sites that are flipped, and I basically label the sites. I label each site with a set of 3 integers, and then I remember that site by taking a polynomial with exponents of those 3 integers. And I superimpose, add together all the terms where there's this cube that's flipped. Let me just give an example. In this case, if I think of this being the origin, this cube is flipping, so I take a 1. This is flipping, which it's going to the left, so that's actually c to the minus 1. Plus this is flipping, so that's eta to the minus 1, plus eta to the minus 1. So why do I do that? I do that because it makes the translational symmetry of the problem clearer. If I want to apply a different sigma z, everything would be translated over in some direction, which means every term should have the same number added to the exponent of each variable, but that's just like multiplied by c to the x, eta to the y, eta to the z. So if I want to apply sigma z at a position r in space, I get the pattern that's this polynomial multiplied by this. Does that make sense? So when I do this thing, I press a button, I get a certain pattern, which I represent by a polynomial. If I label these terms, this could be like 1 with 2 dimensions. right? So that's like C inverse, eta inverse. I press the button, I get the sum of these 5 terms. If I press a different button, I get basically the same 5 terms, but multiplied by C to some power and eta to some power. And if I want to press a whole bunch, each time I press a button, you can think of this pattern as being added to whatever you had before modulo 2. So that's the same as flipping a light from off to on. It's just adding 1 to it, modulo 2. So I take this pattern and add it to whatever was there before. If I press a different button, I get another term added to it. If I press a whole bunch of buttons, the result is just the sum of over all the buttons I press. Times whatever pattern you get from pressing the standard button. Would be like this. So in other words, you can just factor this out. You get a polynomial in C eta and zeta times this particular polynomial. I'm going to always, this isn't standardly a polynomial because I'm allowed to have negative exponents. I'm just going to call it a polynomial. So now I want to explain why it's possible to press one button and then, to press a whole bunch of buttons and get an excitation to move from one position to 3 positions that are either 1 site away, 2 sites away, 4 sites away, 8 sites away, 16 sites away, and so on. So I just want to get some multiple of this polynomial. That's the pattern I get if I press one button. If I press a whole bunch of buttons, I just get some multiple of that polynomial. So I want a multiple of that polynomial that has a 1 here, and then 3 other excitations far away. So the first thing I can do is suppose I square this. Do you know how squaring works, modulo 2? It's like in that. When students first learn algebra, they might think, oh, x plus y squared equals x squared plus y squared.
That's right.
And that's right. Because the cross term is 2xy, which is even. In general, if you're working modulo or prime, you raise it to that power. Working modulo 3 and I cube it, this works. Any prime that works. But anyway, so if I square this, I just get 1 plus c to the minus 2 plus eta to the minus 2 plus eta to the minus 2. And if I square it again, then everything's to the 4th power. And if I raise it to any power of 2, then I just get 4 terms. And all those, what I need is some polynomial times this. And then I'll know that I can get that pattern of excitations. So if I just do this to the power of 2 to the k minus 1, and then multiply it by this, that'll have four excitations. Or if you started with one of the 4 excitations, then you'll end up with 3 excitations. And then the nice thing is if I ignore this term and just multiply this out, and then reduce everything modulo 2, so you either have a term or you won't. Every term that you have on the positions, you should press a button to get this to happen. So this tells you what patterns of buttons you have to press to move the excitations. Okay. So now I want to explain why the excitations can't move. Why are they frozen. So in the case of the layers of toric code, for each layer I have a rule that you just have to have an even number of excitations in that plane. And that means they can't independently move from plane to plane. So I want to have some rule like that in Hus code. But it can't be plane by plane, because if you had a rule for each plane, then, I mean, it could be, for some codes, you'll have a rule for each plane. But if you have a rule for each plane, that says that there's a product of a bunch of these E operators within the plane that gives you the identity. And if I would just not multiply over the whole plane, but over some really big region, that's a big fraction of the plane, everything will cancel out inside, and I'll just have some operation along the boundary. And that, because I have a relationship, the product of the EIs over the whole plane is the identity, which means that if I look at the factors of sigma x, it all cancels out and you just get something trivial. If that were true, if I take a really big region and multiply it together, everything would cancel out on the inside and I just have something around the boundary of that region. But then that operator on the boundary of the region would be a string operator, because it's this operator, it's a non-trivial operator, but it can be written as a product of EIs within in the interior of that curve. And the ground state is invariant under applied EI. So I have it's sort of like Stokes' theorem. I have an operator around the edge that's equal to the product of EIs on the inside, but those give you the identity for the ground state. So I just have an operator along a one-dimensional region that doesn't affect the ground state. And that's exactly a string operator, which means that if that existed, I could just take part of that string. Now, it wouldn't be a perfect identity near the ends, because I messed up the ends. It would create an excitation here and annihilate an excitation over here. In other words, it moves an excitation around. So if it's really true that excitations can't move in Hus code, then there can't be conservation laws in individual planes. But there could still be conservation laws. So let me see how to find the conservation laws. So I want to find a relationship, find conservation laws. I want to find the relationship that says the product of the E's. Right. In Hus code, there's only one per cell that I'll be working with, but alpha index to different E's. I have a product of E's on certain cubes. So I'll represent that by the function. So this G is either 0 or 1 for each cube and for each alpha. And I want to figure out what it has to satisfy. So I have the formula for E over here. If I combine them together, I get that. For everything to cancel out, I need sigma xr to cancel out. So that means G alpha r minus G alpha of r minus d times n d alpha summed over d, and alpha has to be 0 modulo 2. Does that make sense? So I'm basically saying I want to multiply a bunch of these cubes together, and if I look at each vertex, the operators from the different cubes you've multiplied together have to appear each an even number of times. So if I look at this equation, it's kind of like an equation it's kind of like the equation for a mode of an oscillating network of springs to be a 0 mode. I have a bunch of, you could think this is like the displacement, and I have a spring constant matrix, and I multiply the spring constant matrix by the displacement, I get 0. So I want to find the 0 modes. And what is nice about it, this has to be true for every R and every alpha, which is that's a n cubed many linear equations that I have to solve. But it has a translational symmetry. So what should I do if I want to find normal modes of a spring matrix that has translational symmetry? What would I do?
Your transform.
Yeah, use boxing, but take a Fourier transform. So, in other words, I want to take this G alpha of R minus D and take modes in the form of a plane wave. So I assume G alpha of R is A alpha times exponential e to the I theta R. And then I'll plug that into this equation and then solve it. But the problem is, I want integers. I don't want complex transcendental numbers. So I have a problem if I try to take something in that form. So it'll still be possible, but I have to make a small interlude. So now we just go sort of to a different talk temporarily. This talk is called An Introduction to Fourier series with numbers modulo 2. So I need to do that, to make Fourier series modulo 2, I have to introduce a new set of numbers. I mean, it's probably like 100, or it's probably like 200 years old, actually, but they're called, these numbers are called the Galois fields, is what they're called. I think they were discovered by Galois. Or just finite fields. So the first example of the Galois field, you just take the integers modulo 2 and 0 and 1. And that's a field. A field is something where you can add, subtract, multiply, and divide. And you can do all of those as long as you're not trying to divide by 0, which you don't require anymore. That's very simple and silly field. Nice thing is, since it's modulo 2, addition and subtraction are the same. Now I'm going to try to enlarge this and sort of make complex, not modulo 2 numbers. Now I'll take the same method that you do to go from the real numbers to the complex numbers. I'll take an equation that doesn't have a solution in this field, and I'm just going to invent an imaginary number that's defined by the property that it satisfies that equation. So what should I do? I could try to add the square root of minus 1 like I do in the real numbers. Is that a good idea? No, because minus 1 is the same as plus 1, so I already have a square root of minus 1. There's no need to add a square root of minus 1 to the integers modulo 2. So then you might think, like in the complex numbers, once you add the square root of minus 1, you have all solutions to quadratic equations. Like here I have, any square root is in this field. 0 has a square root and 1 has a square root. So it's closed under taking square roots. Then you might think, okay, I have to go to a cubic equation because the equation for a solution of a quadratic just involves square roots. So if I can take any square root, then I can solve any quadratic. But it's not true because there's a 2 in the denominator. So if I take this equation, x squared plus x plus 1 equals 0, that doesn't have any solution because either x is 0 and then you just have one term which is 1, or x is 1 and then you have 3 ones and it So there's no solution to that equation in the integers. But I'll just call, invent something called rho, whose property is that rho squared plus rho plus 1 equals 0. I'll call that rho 2 because it's the solution of a quadratic equation. And then I can make the numbers, call it F4 because there's 4 numbers in this field. A plus B times rho 2 where A and B are 0 and 1. So in this field, I can add and subtract. That's obvious because I'm just like adding the coefficients. And I can multiply because if I multiply two expressions like that, I'll get a rho 2 squared, which I can simplify using that relationship. So this is, and it's not entirely obvious, but you can show you can also divide. Field. I could get a field with 8 elements by taking a solution to a cubic equation that doesn't have a solution already. So I can take something like that, for example. That doesn't have a solution here. And you can also see it doesn't have a solution in F4 because everything in F4 is a degree 2 number. So they can't be solutions of cubic equations. So if I add that to F2, I'll get F8. I'm calling it F8 because I have to take 1 rho 3 and rho 3 squared and take combinations of those. And if I do that, when I multiply any two expressions, I can simplify it down using this relationship over and over again. I have to include one term, every term up to 1 less than the degree of this equation, because this equation only lets you reduce things once they're above that degree. Does that make sense?
ABC is in F4? Or F4?
Yeah, or ABC are in just 0 or 1. I could combine the two together and let A, B, and C be in F4, and then I get something that has 32 elements. And if I do this just for every equation that there is, and combine them all together, I get something called, which has no good name, I think. It just, or it doesn't have a cute name. It's just the algebraic closure of F2. It's just introduce all solutions to algebraic equations modulo 2. And that's an infinite field.
I have a question though. So when you do this extension, is it always, is it always unique? Is the extension always unique? Like,
Yeah, you're saying like, are you saying like, if I take, say, I want to add a 5th degree solution.
Yeah.
There's many 5th degree equations. I could take any one of them. So it turns out that it's unique. There are many 5th degree equations that don't have a solution. But it turns out that once you introduce a root of one 5th degree equation, all other 5th degree equations, solutions can be written as a polynomial in that one root. So that way it's really different than like if I started with the rational numbers and add algebraic numbers, if I add cube root of 2, I can't get cube root of 5 in terms of cube root of 2. But in these numbers, if I add any cubic number, every other cubic number can be written in terms of it.
Is that specific to F2 or?
It's true for any finite. If I take integers modulo 3 or 5, any prime.
Is it can be prime?
Yeah. It can't be a number besides a prime because then it's not a field. Because like if I'm looking modulo 6, 2 doesn't have an inverse. You can't divide by 2 because it's more than 1. Like if I divide 0 by 2, I could either get 0 or 3. So we don't have the digit. So let's see where I am with this. Okay, so now, I wanted to get something that's like exponentials. So I'd like to think of these numbers. So I want to know like which which numbers in this field are the numbers of a unit norm. Because if I don't want something that grows exponentially, whatever that means, maybe we're talking modulo too. But it turns out every number here, in a sense, has a unit norm. So I take x, F2 bar, I'll call it rho. It's in one of these fields, because F2 bar is just the union of all these fields. So say rho is in F2 to the k. Let me take powers of rho. I go rho 1, rho squared, rho cubed, etc. This has only finitely many elements, because they're all just polynomials of a fixed degree in rho. Eventually, I'm going to come back to an earlier element. So, because you can't have an infinite sequence of different numbers. So eventually, two elements will be equal to each other. And then I divide both sides by rho to the a, and I get rho to the b minus a equals 1. So that tells me that every element is a root of unity. If you raise it to a certain power, you get the identity. So every element here, so you can think of rho as being sort of, this is the interpretation, it's not a precise statement, sort of true that rho is e to the 2 pi I times a rational number. If you said equals, I'll say it, analogous to. So if you know from group theory, this if I remove 0, this is a finite group, and any element of the group raised to the order of the group is the identity. So that's a slightly more precise version of the statement. The order of any element has to be a divisor of 2 to the k minus 1. So let me give you a quick application which is not related at all to physics. If you take the Fibonacci numbers and you look at them modulo 7 or modulo whatever you like to look at them, modulo some prime, they repeat over and over again. And the period of the repeat is always either a divisor of p minus 1 or of p squared minus 1. And the reason is that there's this formula for the Fibonacci numbers in terms of the golden ratio. And if I look at this number for a given prime, there might be a square root of 5 modulo that prime without even introducing any imaginary numbers. Like there's a, if I'm looking modulo I don't know, I can't do it right. But like, you might have some number whose square is 5 modulo that prime. So even though square root of 5 isn't rational, it's an integer for certain primes. Convert to an integer for certain primes. Other primes it might not be. You might have to add it, and then you get this field extended by one level. So if I want to look at this number modulo of prime, I can think of this, in the first case, it's just an ordinary integer. And if I raise the integer to a power over and over again, I get back to 1 when you raise it to the p minus first power, because I've gone through every element in the field at that point, and I have to come back to the identity. On the other hand, if 5 isn't a square modulo of that prime, I have to enlarge the field by introducing this as like an imaginary number. And then I'll only get back to the identity after I go through every element of fp squared, which means I have to go through p squared minus 1 elements before I go back to the identity. So that's why, if you look at the Fibonacci numbers modulo prime, you see this pattern. Okay. Good. So if I want to do Fourier analysis, I would take I'm just going one dimension. I just take my amplitude of my wave, then take my sort of complex number, modulo 2, and raise it to the x coordinate. And then I take this. This doesn't make sense because in the end I want something that's either 0 or 1. So just like when you're doing electromagnetism by taking plane waves, but then you take the real part to get an ordinary cosine or sine. So afterward I take the real part. And the meaning of taking the real part is there's a function on this F2 bar that's sort of like complex conjugation. And except that it's not entirely because you have to, it doesn't come back to the identity after one step. You have to apply it several times before you come back to the identity. So the real part is defined as taking a rho to the x plus this complex conjugation function plus phi squared, and so on until it comes back to the identity. And the rule of when it comes back to the identity is if rho is a number in the degree d, if rho is a solution to a degree d polynomial, this will come back to the identity after d steps. You just sum those up and that's like the real part. Yeah.
So A is 0 or 1 and X is an integer.
A can be actually also any number in this field. In the
X
end,
is an integer.
what?
X is an integer.
X is an integer, yeah. Yeah, because X is just the coordinate in space. It turns out you don't really need to think about A's besides 1 because if I change A, it's just like a translation, basically. It's like the difference between cosine and sine.
Sorry, what is phi?
What's that?
What is phi?
It's the complex conjugation function. The equivalent. It takes each element of the field to another element that has the same algebraic properties, like take I2 minus I. So that when you add them all together, you get something that is invariant. If I apply phi to this, phi is linear. So this each term goes to the next term, and because phi to the d is identity, this comes back to the first term. So if I apply phi to this, this comes back to itself, which means it's an integer. Anything that's invariant under phi is real.
So phi is the generator of the outer automorphism group of this field.
Yeah.
Is it uniquely defined by just that statement?
By what?
By just the statement, is the outer automorphism group just like inside?
Yeah. The set of symmetries of that field, the Galois group of that field, it's just a cyclic group. I mean, there's just one. You just need one generator. Actually, I can tell you what phi is. It's a little bit confusing, but it's very simple. It's just phi is some element of the field. It's just the square. It's confusing because I want this to be a symmetry. I want it to preserve addition and multiplication. But you remember that squaring is actually a linear operation, modulo 2. So that turns out to be the complex conjugation in these fields is just squaring. So now we better get to the end. So if I go back to this relation, I want this relation here, and I substitute g of r equals, I'll leave off the coefficient because it's just a linear equation, equals c to the x, eta to the y, zeta to the z. Where c, eta, and zeta, they're not just variables, but they're the actual represent elements of this field. And I plug it into this equation. Then I get c to the x minus dx, zeta to the z minus dz, times n alpha This has to be true for every mu and every x, y, and z. You know, for every one of the two operators on each site and for every position. But I can just factor out c to the x, eta to the y, zeta to the z. And alpha times a alpha equals 0. So if you look at this first part here, once you sum it over D, it's a matrix indexed by alpha and mu. And A alpha is a vector that has to be a zero eigenvector in that matrix to be a normal mode, a zero normal mode. So what this equation says, I have to find a matrix. I have to adjust C eta and zeta so that if it's a square matrix, you have to determine it as 0, or it might not be square. In that case, you want every submatrix to have a determinant of 0, so that there's an eigenvector of eigenvalue 0. So this gives you a condition both on C eta and zeta and on the A alpha. And if you think about it, you can estimate that basically in 2 dimensions, the number of conditions here is enough that the set of possible values of C eta and zeta is finite. You only have a finite number of relationships. But in 3 dimensions, this is enough equation so that there's one free variable, and that gives you a whole family of relationships. So that's why in 3 dimensions it's the first time you get this Haas phenomenon. So for the qubit code, I only have one alpha, so this is just 2 equations, one for each mu. The equations are these 2 equations.
Let me ask a question. So
Yeah.
the psi eta and zeta, you said they are from the F2 part field.
Yeah.
So what if they're 0? Are they allowed to be 0?
Oh yeah, they're not allowed to be 0. Yeah, that's the only number that's not.
They can be any other non-zero, including the extended this row.
Yeah, yeah, it can be any other element. So I want to basically, this would be like if I have a band structure and I want to know where's the energy 0, I get some kind of relationship between exponentials and I solve it. I get polynomial equation basically for the e to the I kx, e to the I ky, e to the I kz. So here's the equation. If I eliminate zeta, I get this. So now I have a bunch of relationships, and I want to prove that defects can't move.
How did you get these first equations?
Oh, this is the same. This is just from this n. That tells me. So basically, I'm taking this plane wave, and I'm for each cube I weight it with either 1 or 0 according to this plane wave, and then I look at a given sigma x and say, from all the cubes that meet that sigma x, does it cancel out or not? So these are basically, if I look here, this, like the weight of this cube, say, is identity. And then if I translate it down, the weight is eta to the minus 1. I want to sum up all those weights and get 0 because there's a sigma x at this point. And then these are the 3 positions where a sigma x can be. So I look at all the ways of translating the cube so that there's a sigma x at that point. And they're weighted, when you shift it, the value it gets weighted with is shifted by a power of C8 or zeta, depending how you shift it. So the first equation is by making sure that sigma x1 cancels out, and the second equation is by making sure that sigma x2 cancels out. You get the product of 2 because the 2's are up there. So I want to prove that the defects don't move. And I actually want to prove even more. I want to prove that sets of defects can't move. That's what's special about. There's some other models where individual defects can't move, but pairs of defects can move. But in the Haas code, no topological defect can move. So let me make that precise. I want to say that if I have a set of defects over here, and it can move an arbitrary distance away without expanding out, this set can move over here while staying in a finite volume. I'll call the distance it moves L. And B is the size of the set of defects. This is possible where B is bounded and L tends to infinity. Then this set of defects isn't topological defect, topological excitations. Then in that case, you can just locally annihilate all of them. You can only move defects an arbitrary distance if you can locally annihilate them and then create them somewhere else without any string in the middle.
So this is the criterion that you can move. This is the moving criterion.
Yeah.
So the toric code, of course, satisfies that.
Yeah. In toric code, you can move a defect with a non-trivial operator, even though you can't locally annihilate that. And this, if you can move a defect, then you can just locally annihilate it.
This layered toric code, this is also possible.
But
The layered toric code.
in the layered
This-
toric code,
Each layer you can do it. So
this is saying you can't do it in any direction at all. So suppose that's so first of all, if I can, so let me prove it's not possible. Suppose I can move a set of defects any distance. There's infinitely many distances that are possible. Any means infinitely many. And that means, but the defects are staying within a finite volume. So that means the pattern of defects has to be repeated sometime. There has to be two different distances where the pattern of defects is the same for both distances. That means there's one pattern of defects which you can translate without rearranging. If it's possible. Would be translated. Now if I can translate defects from here to here, whatever operator does that, I'm thinking of all the operators as products of sigma z's. Maybe you could do something more complicated, but with this Hamilton really pretty clear that adding operators together will just make things worse. So I want to try to move defects from here to here by multiplying certain sigma z's. But if I think about that lights out game, that's like I want to find a set of buttons that turns off these defects and then turns these ones on. But equivalently, if I just start with empty space, if I press all those buttons, I'll just turn on both sets of defects. So if that's possible, that would mean I could create lights here and here, but then I have these conservation laws that says, I have these relationships between the E operators. It says if I multiply all the E's together, with a certain exponent that's given by this plane wave, I have to get the identity. So these positions where the defects are have to be related by the plane wave. So that tells me that if I write it as additive instead of x multiplicative, I have a weight. If I have a defect at position x, y, and z, it has a weight like this. Then I want it. Then this condition over here says if I sum over all positions of defects, I should get 0. So I sum this over all x, y, and z in the first set, and the set on the left, and then I add the set on the right, but that's just a translation. So it'll be c to the a to the b, zeta to the c times the same polynomial. That's equal to 0. And if I factor this, I can factor this. So this has to be true for every c eta and zeta that give you a relationship, which means any c eta and zeta that satisfy these two equations. And let me just I'll say it briefly, and if you want more details, I can explain it more afterward. So if these equations, if this product is 0, one of the two factors has to be 0. That has to be true for every c eta and zeta. So if I look at this equation is two relationships between three variables, which means it gives a curve. Whatever, this part is a little bit not rigorous from a mathematical point of view, because I'm using intuition about real numbers to understand these numbers. But these two relationships define a curve, and maybe it has different components. What we know is that this product is 0 at each point of this curve. But it can't be which means one of the two factors is 0 at each point, and it can't be random. It can't be like this point, this one's 0, this point, the other factor is 0. In any connected component, it has to be one factor or the other factor, which is 0, because these are like continuous functions or something like that. So on each component, there's no continuity. On each component, one of the two factors is equal to 0. So now all you have to prove is that this condition, if this condition were 0 on at least one component, there would be a way to create defects over here and move them somewhere else. Because basically, if I take this, if this is true on one component, I can take a polynomial that's 0 on the other component and multiply it by that. Then I'll get 0 that's something that's 0 identically on this curve. But then, sort of reversing all the logic I did, that says it's possible to create this set of defects. This polynomial describes a set of defects. It's possible to create both that set of defects and the translate of it. There's one funny thing here, which is I'm sort of assuming if all the relationships are satisfied by a configuration, then it's possible to create it locally. And that's not obvious. It's actually, it's a famous theorem of Hilbert that that's true. And also, I think there's some assumptions which may not be true. They think they're true. But on the other hand, the direction we want for the Haas code is if we can just show that this isn't identically equal to 1 on any component of the curve, that means the other factor, if this isn't identically equal to 0 on any component, that means the other component, the other factor is 0 everywhere. But if that's 0 everywhere, that says that the first set of defects all by itself is trivial. That set all by itself satisfies the relation, so it could have been created locally. So all I have to do is show that if I take all the solutions to this, they don't satisfy an equation like this. Let's show.
It should be also satisfied for all possible combinations of ABC.
Yeah, it doesn't have to satisfy for all ABC. You have to show that it doesn't satisfy it for no matter what A, B, and C you take, it doesn't satisfy it. Because if it satisfies it for just one A, B, and C, that means you can translate the set of defects by that A, B, C, and then you can iterate it so you can move it to infinity. So you must show that this is not satisfied on any component. And it looks kind of unlikely that there's a multiplicative relationship between these because these have an additive relationship. But if you want to but you can show it for this high school. There's actually a simple way to do it. This thing, it looks like a circle because it's a quadratic equation. If I think of it as a function of C inverse and A inverse, it looks like the equation of a convex section, but actually it factors. And so you have two linear factors. So this implies either C inverse equals that rho 2 times A inverse plus rho 2 squared, or the same thing with rho 2 and rho 2 squared switched for one of the two components. So this, what I'm saying is this factors into two lines. This describes just two lines. And the equation of the line is C inverse is rho 2A inverse plus rho 2 squared. Then if I go back to the first equation and find what zeta inverse is, it's rho 2 plus rho 2 squared times zeta inverse. So if this relationship were true, that would tell me that A to the B rho 2 A inverse plus rho 2 squared to the minus C times minus A. A inverse to the minus C is equal to 1 identically. And it can't be because you multiply a linear function by another linear function, you just get more and more terms. You don't get one by multiplying them all together. If you like to say it a little more precisely, I don't know if this is more precise. If you want to say it a little differently, this has either a 0 or a pole at a different position than this does, so they can't cancel each other out. So that's how you can show that this Haas code doesn't have possibility to move the excitations. So just to sort of say it in an intuitive way, what we're getting here is we get these plane waves. You could take the real part of them, and that would just be a configuration of ones and zeros in a sort of periodic. It's sort of like a plane wave, but it has some unit. The unit cell is 1. But once you take the real part, the unit cell will be some larger amount, but then after that, you have some complicated pattern of ones and zeros, and then it will repeat over and over again. And this is saying that there's many different wave vectors. And for each of those wave vectors, you have a relationship between all these E's. And this condition that this isn't satisfied says those wave vectors aren't parallel to each other. Because they're not parallel to each other, it's not possible to, or not that they're not parallel, they're not coplanar. And if they're not coplanar, it's not possible to move an excitation, because to move an excitation would have to move parallel to the planes of these plane waves. So if the wave vectors aren't coplanar, then it's not possible to move an excitation. So that's how you can understand it from this point of view. You can also understand that crazy degeneracy from this, using these kind of numbers too. Has to do with the number of solutions to equations like this that are compatible with whatever periodic boundary conditions you have. You basically want a plane wave that satisfies some periodic boundary conditions. That will give you degeneracy. It's interesting to see, to ask, does any of this stuff generalize if you add small perturbations? If it's all topological, it should still work at least if the system is large enough. Do you have more questions?
So maybe we'll thank Ari now. Actually, there is lunch now. So my suggestion is we go and get lunch and we can maybe ask questions there.
Okay,
And also Ari is around for the next few days, I think, till
I think
Thursday.
I'm gonna leave Wednesday morning, so companion tomorrow.
Okay, today and tomorrow, yeah. So he's at he's in the Lyman building. It's like third floor, you're on the third floor.
Yes.
No, your office is on the third floor.